Speech Intelligibility Part 2. From Fundamentals of Acoustics, you get some good points. The result in figures 2.7.3 is obtained with the words and the noise on the dental CD with untrained Danish normal hearing listeners. It is seen that even at a signal to noise ratio of 0 dB, almost all words are understood. It is also seen that an increase of just 10 dB in SNR can change the situation from impossible to reasonable. For instance, from minus 15 dB means 10 dB percent word score to minus 5 dB. It gives 70 percent word score. It is a general finding that such a relatively improvement of the signal to noise ratio can improve the intelligibility situation dramatically for normal hearing listeners. In other words, if the background noise in a room is a problem for the understanding of the speech in a room, then just a small reduction of the background noise will be beneficial. Okay. It is time consuming and complicated to measure speech intelligibility with test subjects. Therefore, measurements and calculation methods have been developed for the estimation of the expected speech intelligibility in a room or on a transmission line. Articulation index AI is a determination of the signal to noise ratio in frequency bands, usually 1 octave or 1/3 octave bands. The SNR values are weighted according to the importance of the frequency band. The weight values are added and the result normalized to give an index between 0 and 1. The index can then be translated to an expected intelligibility score for different speech materials. We have another one, Speech Intelligibility Index SII. I talked about before, about the curve and Lombard effect. This method is based on the AI articulation index principle, but the weighting functions are changed and a number of corrections to the AI method are implemented. One of these is the correction for the change in speech spectrum. According to the vocal effect: shouting, raised voice, low voice. The functions are changed a little bit, and the number of corrections. Then we have the speech transmission index STI. In this method, the modulation transfer function MTF from the source, the speaker, to the receiver, the listener, is determined. The MTF modulation transfer function is determined for octave bands of noise from 125 Hz to 8 kHz and for a number of modulation frequencies 0.63 Hz to 12.5 Hz. The reduction in modulation is transformed to an equivalent signal-to-noise ratio. The reduction in modulation is transformed to an equivalent signal-to-noise ratio. And as in the AI method, these values are added and normalized in order to yield an index between 0 and 1. The index can be translated to an expected intelligibility score for different speech. Okay. Yeah. Okay. Rapid speech transmission index RASTI. This is an abbreviated version of STI, speech transmission index. Only the frequency bands 500 and 2000 Hz and only 9 different modulations are used. Okay, only the frequency bands 500 and 2000 Hz and only 9 frequency different modulations frequencies are used. The result is an index which is used in the same way as STI. Recap simultaneous masking. You have a broadband noise. Then when the frequency below or more than 500 Hz, there will be a 10 dB decrease in SPL per decade from 1000 to 10,000 Hz, or a 3 dB increase in SPL for per octave from 1000 to 2000 Hz, for instance. From below 500 Hz, it's flat, this masking curve. Yes. So we have the low band masking with upward spread masking. When the masking level is increasing, then there's upward spread masking with higher frequencies, towards higher frequencies. For instance, if the masking sound masking is at 1000 Hz, then so for frequencies more than 1000 Hz, signal frequencies for more than 1000 Hz, even far away from 1000 Hz is still need a strong signal. Recap time course of masking. We have this backward masking where we have the signal before masking. This is important from about 20 milliseconds to the masking. Then we have simultaneous masking when the signal and masking are at the same time. And we have a forward masking where the masking is in front of before the signal, and it have a effect it's working up to 200 milliseconds, and this is more than just a signal to noise ratio. What factors characteristic of the channel, and for instance an additive masker could influence intelligibility. We have some steady state versus temporal fluctuations. We have a steady state with a certain amplitude, and we have a modulated masking with a alternating varying amplitude. Assume that both noises have the same spectral energy distribution, also the same dB as per hertz, and equal RMS power. Okay. Which masker is more effective and why? Yes, it is the temporal fluctuations. It's easiest to hear this kind of noise. To hear speech in this kind of noise, because listening in the dips gives some masking release. So we have some number of competing maskers, a number of them with more than a certain amount of babblers, the consonant identification score will be the same percent. Okay, so we have also some informational masking, IM. One definition: any masking or interference that can't be attributed to energetic masking, as we talked about before. Very broad definition means not very specific. Alternative definition: disruption of streaming or segregation of target from background. Yeah. Disruption of streaming or segregation from background. We have room acoustics, direct sound, early rejected, or what's called, and later early reverberance and late reverberance. Yeah, reflection, early reflection or late reflection. Effects on reverberation on modulations. Reverberation reduces the modulation depth, and the gaps are filled in, and that means that the noise has less gaps, reduced listening in the gaps, modulation in target speeds are reduced. So reverberation will decrease the intelligibility. Effect of reverberation on speech intelligibility. If the reverberation time is growing, the speech intelligibility will decrease. Intelligibility drops with increasing reverberation time. Reduction in modulations are detrimental to speech intelligibility. Okay. Spatial hearing and speech intelligibility. Recap from spatial hearing lecture. We have some interoral time differences, ITD, and we have some interoral level differences, ILD. What does that mean? From a sense of hearing, summary. Having two ears help us determine the direction of the sound. There are two such binaural cues, inter or time differentiation. A sound from the right arrives at the right ear first, for instance, and inter or level differences. A sound from the right is more intense in the right ear. Okay. Yes. Interoral time differences are dominant for most natural sounds, but there are some details here. Interoral time differences are most useful for the location of low frequencies. Why? Because low frequencies are what's called diverted, spread more than high frequencies. If the wavelength of a continuous pure tone is less than twice the distance between the ears, if that means that the frequency is a little bit too high, ambiguity arises as to whether the sound is leading to the left or right ear because of phase confusion. However, time differences peaks in a slow varying envelope can be used at these higher differences. Yes. Okay. Yeah. Longer waves diffract more than low frequency waves diffract more than high frequency waves. And then we have interoral level differences arise mainly because of the shadowing effect of the head. Low frequency diffract more than high frequency. So the level Q is most salient at high frequencies. Yes, the difference is more. Thank you. part 2.